Hey everyone. This video is to demonstrate the Coriolis effect. We are going to do this demonstration in class on Tuesday, April 6th. So of course, this video will be available if you miss class that day and you just need to watch the demonstration that you missed, or maybe you just want to revisit it because it was that interesting to you. So what we have here, I have kind of a flat version of Earth, so don't panic. I'm not endorsing flat Earth, but this is going to make it a little bit easier to draw and it will give us the idea of what we're talking about. I also have a Lazy Susan. This is one of those, a lot of people have them in their kitchen. We keep ours on our dining room table. It has like salt and pepper and napkins on it, and it's turned so that people can get to what they need. I also have a cork trivet here that is it's what it's used for pots and pans, but it's going to make a nice thing for us to stick a little straight pin into. And of course, a dry erase marker. So the idea here is to kind of, and just to backtrack a little bit, I guess I should give some context. We in class have been talking about weather and climate, of course, and in that along the way, we've already talked a lot about the deep ocean currents, and we're now talking about convection in the atmosphere. And here's one of those toy squishy globes, the kind that you can, I guess, for stress relief or whatever you can squeeze. I just wanted to show this because today in class, what we talked about were what we call convection cells. And those are these bands of winds that occur at different latitudes along both along the surface of the top and below the equator, above and below the equator. As we discussed, cold air is heavier, so it gets pulled down, displaces warm air, which then gets pushed up. And in the troposphere, which is the layer of the atmosphere that, of course, we walk around in every day, the higher you go, the cooler it gets. And that's largely a function of how thin the air is. It just can't hold heat because there's just not that many molecules floating around up there to begin with. Certainly not as many as there are closer to the ground. So as a result, the air that's flowing along the ground gets warmer. It will then get warm enough to rise, and then cool air will start to fall, et cetera, et cetera. Now, if convection currents were the only thing happening, if these convection cells were the only reason why air moved at all, then all of our winds would either go north or south, depending on what latitude we were at on the globe. But we know that's not true. We've checked the weather. We've seen that we sometimes have winds from the east, winds from the west, et cetera, et cetera. So getting at why winds might not be traveling north and south all the time is where we end up talking a lot more about the Coriolis effect. So the thing about the Coriolis effect, the reason why it is a thing at all is because, of course, we know the Earth is rotating on its axis. We talked about this since the very beginning of the year. And while, of course, the atmosphere travels with it, there's a certain amount of drag. And so the atmosphere is not able to sort of keep up 100% with the spin of the Earth. It's kind of being dragged along behind it. And to simulate that, we're going to look at the Earth just from the North Pole. So that's what this little map shows. This is the North Pole right here, and then this is the equator around the outside. And this little arrow shows the direction that the Earth travels. So the Earth moves like this. Okay. Not shocking. Okay, that's how your day works. So what I'm going to do is I'm going to spin this on. I'm trying to get this as centered as possible here. I'm going to spin this Lazy Susan, and I'm going to try my best to draw just straight lines from the equator to the North Pole. And you're just going to have to take my word for it. I promise you, I'm trying to draw straight lines. It's really hard when you're spinning and drawing at the same time to try to draw a certain shape. So I promise you, this is really the way it works. If the winds were going to try to blow from the equator all the way up to the North Pole. Okay, so let's observe. I'm going to spin. Here we go. Okay. All right. So you can probably see already. See how as it spins and I'm drawing, the line that I draw tends to curve here to the right. Okay. So this is, you might notice this if you did the bell work little activity we did today, you'll notice that this is moving in a counterclockwise curve. Okay, so what's happening then is as the winds are leaving the equator, the Earth is spinning, and so it's pulling, it pulls the wind kind of around in the circle way. So anytime you have these winds that would normally going from south to north, which is what this is showing us, it's going to take the sort of counterclockwise turn. Okay, now we're going to flip this over. I'm going to show you the South Pole too. And it's going to look like I suddenly changed the direction that the Earth is rotating, because now east is going to point this other direction. But that really is, get a globe, try it out for yourself. When you shift to looking from the bottom up, it's going to look like it's rotating in the opposite direction. But this is exactly the way it goes. This is how the Earth spins. Same thing here, and I'm going to draw lines again. All right, let's see if I can get myself steady enough to get started here. Okay, my pen's kind of drying out a little bit. Okay, so now you can see here, same thing, except that we're now hooking the opposite way. Okay, so if we were traveling through here, you would start to see these start to form in more like a clockwise fashion. So as I pull this out, you can kind of see those are hooking more to my left on this side. They're hooking over here to my left. This one is hooking to my right. So this is going in a much more clockwise curve, right? This is the direction an analog clock goes. Although I gather from some of you that you don't read analog clocks that well because you don't have to most of the time, which I get. But the point is, this is why when the southern middle latitudes, when we see these cyclones forming, they typically go in a counterclockwise direction. I'm sorry, in a clockwise direction, down on the southern part of the globe. Okay, so these are the lines. This is what you want to draw in your notes. And of course, email me or contact me if you have any questions about that. All right, have a good day. Bye.